Hello again, welcome to another video. In this video, we're going to learn how to evaluate integrals using one of its method, which is u-Substitution. I promise this video is going to be so fun, so let's start. First of all, when we're dealing with integrals, we have to know that there are two types of integrals. The first one is indefinite integral, and the second one is definite integral. Well, the difference between these two is as follows. So if I want to write a general form of these two integrals, it would be as follows. So it would be integral f of x dx, and the definite integral going to be the same thing, f of x dx, but the difference is that the indefinite integral, it does not have bounds of integration. It does not have limits, whereas the definite integral, it has a lower bound and an upper bound of integration. Plus, when we are dealing with indefinite integral, so the answer going to be in terms of x. So if I have the function in terms of f of x dx, the integral, the evaluated integral, going to be in terms of x, in terms of the variable x, plus a constant c. But where we're dealing with a definite integral, the answer of the evaluation going to be a number. So this is the difference between these two types of integration. So let's now try to know and understand what does u-Substitution mean. U-Substitution mean that if you see some complicated things, complicated expressions in an integral, try to replace it with the letter u and make the process of integration easier for you. This is the same as when you want to text a message to a friend, you use acronyms, you use abbreviations. So instead of you use like you write or you text a friend good morning, you text GM, and your friend and yourself know that what does GM stands for. So this is only to make the process easier. This is the same thing here. We're not trying to change the problem, but we are trying to look at the problem in a way which is easier for us to evaluate and deal with. So this is the whole purpose of using u-Substitution. So let's try to see how we can do it. So especially we use u-Substitution when we see a function inside a function. So here where we use u-Substitution, and we use it in some places where we see there is an expression inside the integral, plus we also can see its derivative inside it and beside or nearby to that expression. So let's see an example to understand what I'm saying. So look at here, I said we use u-Substitution when we see a function inside a function. Here I can see a function which is really not kind of weird, but it's kind of long, which is this one right here, x squared plus 1. And I also can see its derivative inside it, inside the same integral, which is 2x. So I go to starting. How can I do it? Well, I would say that let u be this function, which is x squared plus 1. Then I'm going to take the derivative of this u. I'm going to say du is equal to 2x, right? And I also have to put the dx because we are taking the derivative to respect to x. So this is everything. Now I can see the 2x right here. I can also see dx right here. So I can rewrite the integral as follows. So we are replacing this expression x squared plus 1 with u, and we are replacing 2x dx with du. So it's going to be as follows. So it's going to be integral u to the 5 du, and that's all. Now we can evaluate this one because we made a long expression, a long integral, to a short one, and perhaps we can solve the integral or kind of evaluate the integral for the short term. So this is going to give me 1 over 6 u to the 6 plus c plus a constant number. I'm going to explain why we use the constant number right here. So now when I found this expression, this is not the last answer because this is in terms of u and my integral is in terms of x. So after finding the evaluated form for u, now I have to back substitute to find this expression in terms of x. So I said here, let u be x squared plus 1, right? The only thing is replace u with x squared plus 1. So I'm going to get 1 over 6 x squared plus 1 to the 6 plus a constant value. This one going to be the answer to my integral, and that's all. Let's move to the next question. So, a function inside a function. So if I look at cosine 3 to the x as a function, this 3x is inside the whole one. So if I have f of x is cosine of x and g of x is 3x, then f of g of x going to be cosine 3x, right? So it's kind of like a function composition. This is the same thing. So I can replace 3x with u. And if I take the derivative of it, it's going to be 3. And it's dx. Wait a second. I said I can see the derivative inside the integral. But it does not really necessarily have to be the same thing. Now here, I can see the dx, right? Which is here, but I can't see the number 3. So the thing that I'm going to do is, I would say that dx is equal to 1/3 of du, right? Now everything is good. And let's see what can I do next. So I can rewrite the integral as cosine of u, right? And cosine of u is not enough because we are changing the dx into 1/3 du. So I can move this 1/3 back to the integral or in front of it, so it does not really matter, but it's preferred to kind of move it back to the integral. So now I can evaluate this one. So this one going to be 1/3 times sine of u plus a constant number. But now the integral is in terms of x. This is not enough because this is in terms of u. I have to back substitute it to get the evaluated form in terms of x. So this is going to be 1/3 sine of 3x plus c. And the problem is solved. So let's move to the next one. Right here, the thing that really bothers me is this x to the 4. Oops. So this x to the x plus 4. So I can say that let u be x plus 4 and du is this going to be 1, so I can ignore it. Du is equal to dx. And I can rewrite this as integral, and instead of 1 dx, I can write du over u. Or it can be integral 1 over u du, and we know that ln of u plus c is the answer to this one. Now I can back substitute. My u is x plus 4. I can write it as ln absolute value of x plus 4 plus a constant c. This is the answer. Now right here, the thing that it bothers me is 5x. I know the integral of e to the x, but I don't know e to the 5x for now. I can rewrite 5x as u. So I can say let u be 5x and du is 5 dx. I have dx right here, but I don't have the 5. So I can say dx is du over 5 or 1/5 du. So I can rewrite the integral as 1/5 e to the u du. So the thing is, we replace dx with 1/5 du. I move the 1/5 back to the integral, so it's here, and du is right here. And instead of 5x, I just replace it with u, so I can see it as my exponent. And now I can evaluate this one perhaps because I know the integral of e to the u. So it's going to give me 1/5 times a to the u plus c. Now I have to back substitute, and it's going to be 1/5 times e to the 5x because my u is 5x, and now I have to back substitute u, so I'm going to get e to the 5x plus c. So for now, we're done with our indefinite integral. Now we see the same examples, 2 of them in right here, and the last one as definite integrals, and we're going to see the difference between these two. The thing is, now I can see the bound of integration. Now I have the limits of my region where I'm taking the area of that. So what is the difference? So the first thing is I can take this one right here, take this one right here, without the c perhaps, because the definite integrals is going to be in terms of a number only. So I just took it right here, and then I can evaluate this one as when it's from 0 to 1. So when we're dealing with definite integrals and we found the general expression, like the evaluated form in terms of x, and I have the definite integral, I just simply, after that, I just drew a line and put the bounds. So it's from 0 to 1. And how can I evaluate it? This is so simple. So I'd say 1 over 6. Just put 1 inside this. It's going to be 1 over 6 times 2 to the 6 minus 1 over 6. If I put 0 here, I'm going to get 0 plus 1. It's going to be 1 to the 6. So this is going to be the answer. So 2 to the 6 is, I believe it's 64 or 816. Yeah, it's 64 over 6 minus 1 over 6. So the answer is going to be 63 over 6. But is there any other way to do it? Yes, there is. If I just want to forget, but I say it right now and start from the beginning, I can do in another way. So the first steps are pretty much the same thing. So it's going to be let u equal x squared plus 1, and du it's going to be 2x dx, right? And I'm going to write the integral. Now I have 2x and dx. I can replace it with du, and x squared plus 1, I can replace it with u. So it will be u to the 5 du. How about the limits? How about the bounds? Well, these bounds are in respect to x, but now we change the whole thing to u. So the limits also have to be changed to u in terms of u, or to respect to u. So this is my x in terms of x, but now I said u is equal to x squared plus 1. So I just simply throw an arrow right here, and then two things. I have the lower bound in terms of u and the upper bound in terms of u. So if I just simply replace x with 0 to get the u, it will be 0 squared plus 1, which is 1. And the upper bound going to be 1 squared plus 1, which is 2. So now my lower bound of the integral of u to the 5 du is going to be from 1 to 2. Now let's evaluate this one. So this one here, it will be 1 over 6 u to the 6, and the integral is from 1 to 2. So now let's work on it. So now it will be 1 over 6 u to the 6. So we start with the upper bound and replace it with u. This will be 2 to the 6 minus the lower bound, which is 1 over 6 u, and instead of u, just replace it with 1 and to the 6. So this would be what? 2 to the 6 is 64 over 6 minus 1 over 6, which is 63 over 6. The same answer as we got before. It doesn't matter. You can do it in either way. Let's do the last one. This one, as we did before, I'd say let u be 5x and du be 5 dx. But since we don't have 5 right here and only we have dx, I would say dx is equal to 1 over 5 du. So I can rewrite my integral as follows. It's going to be 1 over 5 integral e to the u du. Now, these bounds, these limits are in terms of x. Now I have to change it to u. And u is equal to 5x. So the only thing that I have to do is just plug these numbers, these bounds, into this one. So if I plug 0 into this one, I'm going to get 0, and 1 into this one, 5 times 1, it should be 5. So let's evaluate this one. So this will be 1 over 5 times the integral of e to the u is e to the u, and the integral is from 0 to 5. So this would be what? 1 over 5 times e to the 5 minus e to the 0. E to the 0 is 1. So I can simply write it as 1 over 5 times e to the 5 minus 1. And this is the answer. Well, the difference that is here with the previous one is that we didn't have to back substitute. We just simply could just evaluate the integral because we already changed the bounds and we made them in terms of u. So we didn't have to go back away and do the back substitution to evaluate the integral. So just you can do it in either way, it does not really matter. And back to the thing that I said is, why do we actually put the constant c? The thing, or the fact that we use the constant c, is because let's say that I have f of x is x squared plus 3, and I have g of x, which is x squared plus 5, and I have k of x, which is x squared negative 2. Now if I want to find the derivative of these numbers, so it's going to be f prime of x, and I want g prime of x, and I want k prime of x, well, let's try to find them. So the derivative of this one going to be 2x, the derivative of this one going to be 2x, the derivative of this one also going to be 2x, right? Or not, because these are constants, and the derivative of a constant number is 0. So I have the derivative right here, and now if I want to take the integral of 2x dx, it should be x squared, right? But how about these numbers? What will happen to these numbers? We actually have a number, so x squared is not the same as these ones right here, and I cannot say x squared plus 3, which is wrong. So we perhaps need a constant number here. So instead of any number, or instead of leaving it empty, I put plus c, and this c could be any number. It can be 0, it can be a negative number, it can be a positive number. So this is the idea about using a constant c into evaluating integrals. And this is pretty much about using the substitution method, and I hope you liked it. Please let me know if you need any other topics, and give me a feedback on this. We'll see you next video. Have a good day.